Hi students! Today we're going to be going over Module 4 homework assignment, and this module goes over transformations, symmetries, and tilings. So if you would, go ahead and pull out your homework assignments, and I'm going to walk through each question and give you a detailed explanation as to how to do each one. So let's just go ahead and get started with question 1. This question says, two boys were asked to reflect the figure on the left over the horizontal line through the center of the square. They rearranged the blocks to form the figure on the right. What type of motion did they use? So as you can tell, they started with this figure right here on the left and they ended up with this one. But they did not end up reflecting the figure over the horizontal line through the center of the square. Instead, they kind of did this rotation right here. And it led them directly to here. So as you can tell, this figure, it just flipped all the way around 180-degree rotation. So that's what this is. They did a 180-degree rotation, not a reflection over the horizontal line through the square. Now part B wants us to find out what the corrected solution should look like. So here we go with our figure again, and here's the line that it should be reflected over. So what this means is if we took a piece of paper and drew this figure on it and we folded it on this line right here, that means that whatever is up here will just transfer it down here. So this point should be directly all the way down here. So when we do that, when we reflect it over that line, that's what that looks like. So this point moved all the way down, and you can see that illustrated right here. So that's how the figure should have looked like. Now question 2 gave us a few different shapes, and they asked us a series of questions about those shapes. So the first question wants to know, out of those shapes, which ones had one line of symmetry but no rotational symmetry? This is the first figure. We have an equilateral triangle, and this triangle does have a line of symmetry, and it has others as well, but you only need one line of symmetry to be symmetrical. So this figure, it meets the qualifications for one line of symmetry, but when you rotate this figure 180 degrees, so if we take the top of this point and rotate it down here 180 degrees, this is what it will look like. So it does not match up perfectly with this one right here. So that's how you know it doesn't have rotational symmetry. Same with this shape, a chord. This has one line of symmetry going straight down the middle, but when you rotate it 180 degrees, it looks like that. So it should have the flat part at the top, but instead it has the flat part at the bottom. So since it doesn't line up perfectly with the first image, it doesn't have rotational symmetry. And same with this triangle right here. It has a line of symmetry right there, but when you rotate it 180 degrees, it looks like that instead. So the point should have ended up on the right side like it began, but instead it ended up being on the left side once it was rotated. So that's how you know that figure doesn't have rotational symmetry either. Now the next part of this question wants us to look at shapes that have rotational symmetry but no reflection symmetry. So this is the first shape we have, and if you draw a line such as this one, and if we folded it along this line right here, the line of symmetry, it would not, the lines and the edges would not meet up perfectly. This would be down here and that would be up there, so it would not match up perfectly. So we know that that doesn't have reflection symmetry. And even this line, if you were to fold it along this line right here, it still wouldn't meet up perfectly. So we know for sure that this figure does not have reflection symmetry. But when you rotate it 180 degrees, it looks like this. And that looks exactly like this first picture right here. So that's how we know that this has rotational symmetry. Now the next figure is this one right here, and just like the first one, this doesn't have reflection symmetry either. If you fold it on this line right here, the lines aren't going to meet up perfectly. And neither is it going to line up perfectly if you fold it on this line. It's just not going to happen. So this figure doesn't have reflection symmetry. But once again, if you rotate this 180 degrees, it turns out to look exactly like it did from the beginning. So that's how you know that it has rotational symmetry. Now this last part wants us to look at the figures that have one line of symmetry and rotational symmetry. So this is the first shape, and this has one line of symmetry, and it has other lines of symmetry, but we're only looking for one because if it has one line, it's automatically symmetrical. So you could put other lines on here, but I just drew this one. Now when you rotate it 180 degrees, it's going to look exactly the same as this shape. Next we have the rectangle, and once again this has a line of symmetry. You could also draw one going this way, going diagonally, but I'm not going to put all of those lines on there because it's automatically symmetrical if it has one. But when you rotate this figure 180 degrees, it turns out exactly like this one does. And the last figure is the hexagon. And this also has one line of symmetry. It also has a ton of other lines of symmetry. Y'all should check it out. But when this figure is rotated 180 degrees, it turns out to be the same as this shape right here. So that's how you know that all of these have one line of symmetry and rotational symmetry. Now moving on to question 3. Myra cut out a regular pentagon, hexagon, and octagon, and it seems to her that they form a vertex figure. Is Myra correct? Well, when you first take a look at this image, it looks like Myra is correct because to be a vertex figure, there can't be any gaps between the shapes and they can't overlap. So right here, this is where it forms the vertex. And they're not overlapping, and there's also not any gaps. So it looks like she did it perfectly. But when you continue that process and add the shapes like they're supposed to be, you can see how they overlap. Like down here, they're overlapping a little right here, a little right here, and you can definitely see it right here. So Myra was very close to coming up with a vertex figure, but I don't think she thought it through since it had to go all the way around and complete a pattern. So no, she did not create a vertex figure. Now, for question 4, we're asked a series of questions that you have to look at this image to answer. Now, the first one wants to know if triangle QPT is congruent to triangle SPT. Now, the problem also gave us this right here. These lines mean that these two lines are the same and these two lines are the same. So when you look at triangle QPT, this line is exactly the same as this line in triangle SPT, and same with this line and this line. That means they're the same, and they also share a line right here. So if all three lines are the same, that means that those two triangles are congruent. Now, same with the angles, part B. The angles of QPT and the angles of SPT are also congruent because if the lines are congruent, if they're all the same, that means the angles are going to be congruent as well. Now it asks, why is triangle QPV congruent to triangle SPV? Well, this is kind of the same concept. We already know that these two lines are the same measurements because they're congruent. They share this line right here, so we know that's going to be the same. And this line right here is met in the middle of these two congruent lines. So that's how we know that these two triangles right here, since this line is in the base of them, that's how we know that those two triangles are congruent as well. Now it wants to know why angle QVP is a right angle, and this one's super easy. Anytime that there is a vertical line and a horizontal line, or you could say perpendicular lines that meet, just like this, they're always going to form a right angle no matter what. So that's why QVP is a right angle. Now moving on to question 5, we are given this circle, and there is a pentagon inscribed inside of the circle, and these are the points. Isn't it clever they named it penta? I think that's pretty cool. And they also inscribed a triangle, which is PQR, and they all have a center point of O. Now here's where the measure of NOQ comes in. So we've got to find out what the measure of this angle is. And in order to do that, we're going to find the interior angles of the pentagon first. So we know that the pentagon all around is 360 degrees, and since there's 5 angles within the pentagon, we're just going to divide 360 divided by 5, and that equals 72 degrees. Next, we're going to do the same thing for the triangle, and we know that the triangle equals 360 degrees, and since there's 3 angles inside of the triangle, we're going to divide 360 by 3, and that equals 120 degrees. Now we're just going to subtract 120 minus 72 from the interior angles from the pentagon and triangle, and we get 48 degrees. Now this part is kind of confusing, so you really need to make sure you know why we do this part. But we were looking at 360 degrees for the pentagon and the triangle. But if you look at angle NOQ, this meets at center O. And this right here is the radius. So we know that O, which is one of the points in the angle, is at the radius. So we know that the diameter, which goes all the way across, is double the radius. So that's kind of what this is. This is almost like the diameter in a way. So you're going to divide this by 2 because we're not looking at the angle all the way across. Okay, we're looking at the angle that stops in the middle at the radius. So we're going to divide 48 by 2, and that equals 24. So that means that the measure of angle NOQ is 24 degrees. Now the last question wants us to find out how Jenny can measure the height of the cliff. And here's that image for you. Here's Jenny, and here's the cliff. She's trying to figure out the height of it. Now here's what we know from the problem. We know that the ruler, which is right here, is 2 feet in front of Jenny's eye. So she's holding it out 2 feet in front of her. Now the top and bottom points of the cliff, so right here, the top and bottom of the cliff are only 1.5 inches between ruler markings. So when she's looking at it on the ruler, it's only 1.5 inches tall. Now Jenny is 1/4 mile away from the cliff when she is taking these measurements, and they also tell us that 1 mile equals 5,280 feet. So we're going to outline that triangle that she's looking at right here. I've outlined it, and there's also another triangle that we've got to take into consideration, and it's this one right here. It's the triangle from Jenny's eye to 2 feet in front of her. So we've got to take into consideration both of those triangles while doing these calculations. Now here's the formula that Jenny's going to use to measure the height of the cliff. This formula is the distance between ruler markings divided by the distance from eyes to ruler. And this equals the height of the cliff divided by the distance from the cliff. Now we're going to just plug in what we know. So the distance between ruler markings is 1.5 inches, and we're going to divide that by 2 feet, which is the distance from ice to ruler. And this is going to equal height of the cliff. And we're going to divide it by distance from the cliff, which is a 1/4 mile, since Jenny is a 1/4 mile from the cliff. Now, in order to finish this calculation, it'd be easier if we got all of the units the same. So we're going to convert inches and 1/4 mile right here to feet. So when we do that, we get 0.125 feet, and then we divide it by 2, and then we get height of the cliff divided by 1,320 feet, because we're taking what 1 mile equals and we're dividing it by 4 so that we get that 1/4 mile. We're not looking for the full mile, but just a 1/4. So that's why we divide this number by 4 and we get 1,320 feet. And this gives us the height of the cliff equals 82.5 feet when we do those calculations. So that means that the height of the cliff that Jenny is looking at is 82.5 feet, and this could be rounded up to 83 feet as well. So that is the end of the homework assignment. If y'all have any other questions, feel free to reach out to me. I would love to answer those questions for you. But I hope that this video was helpful for you all, and I hope that you each have a great night. It's almost summer. Just stay in there. We're almost to the end, you guys. Well, I hope that y'all all have a great night, and I will see y'all later. Bye-bye.